The Fibonacci numbers form a recursive sequence where the first term is 1, the second term is also 1, and the nth term is going to be the sum of the previous two terms, namely the n minus first term and the n minus second term. And this happens for all n greater than or equal to 3, and n is going to be a natural number. Okay, maybe I'll do it like this: 3 less than or equal to n, which is an element of the natural numbers. Okay, so I'll go through some questions involving induction. The first one is proving, using induction, the sum from k equals to 1 to n of fk squared, and this is equal to fn times fn plus 1 for all n in the set of natural numbers: 1, 2, 3, 4, 5, 6, so on and so forth. The proof goes like this. We need to establish the base case first, namely n equaling to 1. This implies that the sum from k equals to 1 of fk squared, and this is just equal to f1 squared. It's just the first term. f1 we know is 1, so 1 squared is just equal to 1. And we also know that from the right-hand side, we have f1 times f1 plus 1, f2. They're both 1, so 1 times 1, 1 squared is 1. And this implies that base case holds. So now we have the induction step. Suppose that the sum from k equals to 1 to n of fk squared, this is equal to fn times fn plus 1 for some arbitrary natural number n. Then the sum from k equals to 1 to n plus 1 of fk squared is equal to the sum from k equals to 1 to n of fk squared plus that last term, which is going to be fn plus 1 squared. And this is equal to fn times fn plus 1, okay, by the induction hypothesis, which is this over here, okay, plus fn plus 1 squared, okay, fn plus 1 squared, fn plus 1 squared. And this, if I factor out fn plus 1, I'll get fn plus 1 times fn plus fn plus 1, but this part right over here is equal to fn plus 2, okay? Because fn plus 1, these two terms, by our definition for the recursive relationship of the Fibonacci numbers, we get fn plus 2, which implies, this implies that the induction step holds. Therefore, by the principle of mathematical induction, the sum from k equals to 1 to n of fk squared is equal to fn times fn plus 1 for all natural numbers n. Next, the sum from k equals to 1 to n of fk, this is equal to fn plus 2 minus 1 for all natural numbers n. Proof. Base case is when n equals to 1. So this implies that the sum from k equals to 1 of fk, this is just f1, which is 1. And f1 plus 2 is 3 minus 1. f3 is going to be, well, what's f3? f3 is equal to f2 plus f1. 1 plus 1 is 2. So f3 is 2 minus 1, which is 1, and 1 is equal to 1, which implies that the base case holds. Now, for the induction step, suppose that the sum from k equals to 1 to n of fk is equal to f n plus 2 minus 1 for some arbitrary natural number n. Then we have the sum from k equals to 1 to n plus 1 of fk is just the sum from k equals to 1 to n of fk plus fn plus 1. So this right here, again, is my induction hypothesis. And if I use that over here, I can say that this is equal to fn plus 2. Okay? And then over here, I have to add my fn plus 1. Okay? Fn plus 2 minus 1. Okay? And then add fn plus 1. But again, fn plus 2 combining with fn plus 1 gives me fn plus 3. So these two gives me fn plus 3, and I have a minus 1 left. And this is what I want. So this implies that the induction step holds. Therefore, by the principle of mathematical induction, the sum from k equals to 1 to n of fk is equal to fn plus 2 minus 1 for all natural numbers n. Now, proving that fn is greater than or equal to 3 over 2 to the exponent of n minus 2. This is true for all natural numbers n. Proof. Number 1, we have to establish the base case again. N equals to 1. This implies that f1 is equal to 1 and 3 over 2 to the exponent of 1 minus 2, which is negative 1. So we get 2 over 3. So this implies that f1 being 1 is greater than or equal to 2 over 3. Okay? So this implies that the base case holds. For the induction step, suppose that fn is greater than or equal to 3 over 2 to the exponent of n minus 2 for some arbitrary natural number n. Then fn plus 1 is equal to fn plus fn minus 1. The problem I run into now is this right over here. And the reason why is because if we go back to the definition, f something, okay, this something needs to be at least 3, okay? So here we have the something, namely being n plus 1. So we need to have that n plus 1 is greater than or equal to 3, or we can say 3 is less than or equal to n plus 1, which means that n is at least 2. And because of that, my base case is not enough, because my base case has n equals to 1. So I cannot really use this right over here, because in order for me to use this, I need to have n to be at least 2. What to do over here? And that is where the strong induction comes in. So rather than having base case, we have base cases, which are n equals to 1, and this implies that f1 is equal to 1, and 3 over 2 to the 1 minus 2 being negative 1 is equal to 2 over 3. We did this already. f1 is greater than or equal to 2 over 3. That's good. Okay? And when n equals to 2, okay? Because remember, when we had to use that fn plus 1 is equal to fn plus fn minus 1, that n has to be at least 2. So let us have two base cases, n equals to 1 and n equals to 2. We get that f2 is equal to 1, and 3 over 2 to the 2 minus 2, which is 0. 3 over 2 to the exponent of 0 is equal to 1. And this implies that f2 equaling to 1 is indeed greater than or equal to 1. So that works. this implies that the base cases hold. So now comes the induction step. Suppose that Fn is greater than or equal to 3 over 2 to the n minus 2 for all 1 less than or equal to k less than or equal to n for some arbitrary natural number n that is at least 2. So we are claiming that it is not only true for the nth term, but all the terms below the nth term. Then, what is Fn plus 1? That is equal to Fn plus Fn minus 1, and that is greater than or equal to 3 over 2 to the n minus 2 with this, plus 3 over 2 to the n minus 3 with this. If I factor out an 3 over 2 to the n minus 1, then I get 3 over 2 to the minus 1 plus 3 over 2 to the minus 2. And why do I want that? The reason why I want this is because I have a 3 over 2 to the n minus 1, and that's a step more than 3 over 2 to the n minus 2. Solving this using common denominators and combining the fractions, I get that this is equal to 10 over 9. So I have 3 over 2 to the n minus 1 times 10 over 9. And 10 over 9 is a number greater than 9 over 9, which is 1. So it will be greater than 3 over 2 to the n minus 1, which implies that my Fn plus 1 is greater than or equal to 3 over 2 to the n minus 1 due to the transitivity of these inequalities. Okay? And this is good. This implies that the induction step holds. Therefore, by the principle of mathematical induction, and it will be strong induction in this case, the previous two examples were weak induction, Fn is greater than or equal to 3 over 2 to the n minus 2 for every natural number n.